Now, what if you have more than one electron? So far, we talked about H2 plus. We did talk about H2 also. The same idea, you have molecular potential energy. You can calculate molecular potential energy for any molecule. But typically, when you're dealing with molecules, you're interested in the most stable form of the molecule. Not in the case of a diatomic molecule, you're interested really more in the geometry here, where you have the minimum in your electronic energy for the ground state. Okay, so you look at the possible wave function in those situations. Generally, what you do in case if you have more than one molecule, just like in atoms, when you have a one electron atom, our wave function is a function of one electron, right? In a molecule with more than one electron, in a molecule with one electron, your wave function is a molecular orbital, a function of the coordinates of one electron. If you have more than one electron, then you have to have a function of more than one electron. And again, the issue of indistinguishability of electrons and Pauli's exclusion principle has to be taken into account. And so you can express your wave function then as just a Slater determinant of molecular orbitals. Instead of Slater determinant of atomic orbitals, you use molecular orbitals. A common technique for constructing molecular orbitals uses what's called the LCAO method. LCAO stands for linear combination of atomic orbitals. Here it is, linear combination of atomic orbitals. Okay, and so you construct your molecular orbitals from the atomic orbitals of the molecule. You just take linear combinations of those, and so different atomic orbitals will contribute different amounts to the linear combination. So you're going to say, your molecular orbital would be equal to C1 AO1 plus C2 AO2 plus C3 AO3 and so on. Where AO1 is the function for atomic orbital number 1, AO2 is the function for atomic orbital number 2, AO3 would be the function for atomic orbital number 3, and so on. C1, C2, and C3 are just the coefficients. So they have different contributions to the molecular orbitals depending on the symmetry of the molecule. Okay. A molecular orbital diagram summarizes how the molecular orbitals for the equilibrium geometry are related to the atomic orbitals. So you can set up a diagram that sort of allows you to visualize where the molecular orbitals come from which atomic orbitals did you get those molecular orbitals. It's a good way for us to visualize what's going on when atoms form molecules. Okay, so the molecular orbital that has lower energy than the contributing atomic orbitals, we call those bonding orbitals. And molecular orbitals with higher energy than the atomic orbitals that contribute to it would be what we call anti-bonding orbitals. Okay? And like I said, the anti-bonding orbitals are denoted by a star next to the name. Okay? Now, the names of the molecular orbitals for diatomics, just like H2 plus, are given by sigma, pi, delta, and phi, and so on. For polyatomic molecules, the names are typically you'd encounter names like A, B, E, T, A1, B1, A2, B2, and E. Okay, and you'll have labels like G for gerade and ungerade, and things like that. And it all depends on the symmetry properties. Okay, so you'll learn more about that when you get to your inorganic chemistry, Chem 412, Advanced Inorganic Chemistry. So let me show you an example of a molecular orbital diagram. This thing right here for fluorine, ChemTube 3D. Just search for ChemTube 3D. Let me see. Molecular orbital. Fluorine, for example. There it is. My Java is out of date. Run this time. Okay, here's an example of a molecular orbital diagram. Okay, down over here you have an energy level diagram arranging those orbitals in order of increasing energy. So in the case of fluorine, the lowest energy molecular orbital is known as the 1s sigma. Okay. And it's what are the atomic orbitals that contribute to the 1s sigma? The 1s orbital of one atom, call it atom B. So fluorine, you have two fluorine atoms. You can call this one atom A and atom B. The other one's atom B. So you have a linear combination of 1s orbitals from both atoms can give you a bonding sigma orbital that's lower in energy. Or a linear combination of those two could also lead to an anti-bonding orbital. Generally, if you do 1sa plus 1sb, okay, so you have a 1s orbital here and a 1s orbital here, they add up, you build up electron density between the two nuclei, and that just generally leads to what we call bonding. Okay. Now, if you have 1sa minus 1sb, what happens? Change the sign for the 1sb to negative. So this is negative and this one's positive. So what happens when positive and negative combine? You get a node in between the two. You have an anti-bonding orbital. So this is 1s sigma star right there. There's a star in the name. Okay? Let me see if I can get something. Show the 1s sigma. There's the 1s sigma. Okay. And if you do the 2s sigma, so a linear combination of the 2s orbitals of the two atoms would give you this sigma, 2s sigma orbital. Okay, and then you have 2s sigma star, and then a p orbital on both atoms, a pz orbital. Okay, remember this is your z-axis, right? So if you have a p orbital here and a p orbital here, that gives you a 2p sigma molecular orbital, that particular linear combination. Let's see. So the 2p sigma, let's show p 2p sigma. Right there. So you can see there isn't a node between the two nuclei there. Okay, so there's a high electron density between the two nuclei. So that's a sigma orbital formed by a 2p on one and a 2p on the other. Okay. I think this is going to be, if this was A and that's B, and then this is going to be 2pa minus 2pb, because 2p pz orbitals, because then this will be plus minus, and then you have to flip the other one to minus plus so that they build up electron density in between. Okay. So these are your, so that's your energy level diagram, okay, for your molecular orbitals of fluorine. Let me see if I can find one for you for water. Molecular orbital diagram for water, this one here. Let's see, lsbu.ac. Okay. Molecular orbital diagram for water. lsbu.ac.uk. This one right here. These are your molecular orbitals for water. The lowest energy orbital is the 1A1, the first A1 or molecular orbital, the second A1 orbital, the first B2 orbital, 1B2, and the next orbital is 3A1. Okay, what's contributing to the first A1 orbital? It's primarily coming from the 1s orbital of oxygen. So what we're saying here is what we call the first A1 orbital of water is essentially the 1s orbital of the oxygen. Okay, what about your 2A1? You got contributions from the 2s orbital of oxygen. Did I say oxygen or hydrogen? Oxygen, yeah. And then you have contributions from the 1s orbitals of the hydrogen. Okay, we'll give you the 2A1, and then you have the 1B2, and so on. Okay? So these are the molecular orbitals of water. Bond order. A molecular orbital diagram is useful for determining what we call bond order. And essentially what we mean by bond order is if bond order is 1, we say that there's essentially a single bond between the two atoms, the two nuclei. Bond order of 2 means you have a double bond. Bond order of 3 is a triple bond. Okay? So if you have a positive bond order, then you expect to get a stable bond between the two nuclei. All right, so bond order is just the number of bonding electrons assigned to bonding orbitals minus the number of electrons assigned to anti-bonding orbitals. If there are more electrons in the bonding, divided by 2. If there are more electrons in the bonding orbitals, then you say you expect the two nuclei to form a bond, the two atoms to form a bond. And you can predict that using Pauli's principle by assigning electrons to orbitals. And same rule. 2 electrons per orbital maximum, one spin up, the other one spin down. Okay, so let's try that for, let's say, fluorine and determine the bond order for fluorine. Here's the molecular orbital diagram for fluorine. How many electrons does a fluorine molecule have? F2. Fluorine has how many electrons? 9 electrons, so times 2, 18 electrons. Let's assign those electrons. So 1s sigma, you can put 2 electrons, one spin up, the other spin down. 1s sigma star, one spin up, one spin down. That takes care of 4. How many more to go? 14 more to go. 5, 6, that's 2 more in the 2s sigma. And then 2 more in the 2s sigma star. That takes care of 18. The 2p sigma, that's 2 more, that's 10. Okay, 2p pi. You'll notice, remember we said pi orbitals are doubly degenerate, right? So they come in sets of 2, you might say. So, oops. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you follow Hund's rule. 11, 12, 13, 14, 15, 16, 17, 18. Okay? How many bonding electrons do we have? Our bonding orbitals are this one, that's 2, 4, 6, 8, 10. That's 10, right? 10 electrons in bonding orbitals. How many electrons in the anti-bonding orbitals? You have 2, 4, 6, 8. So 10 minus 8 divided by 2. Bond order is 1. We expect the bond between the 2 fluorine atoms to be a single bond. Now, the diagram for O2 is going to be similar. Okay? And so what would be the bond order for O2? If we were to do O2, how many electrons do we need? 8 times 2, 16 electrons. 2, 4, 6, 8, 10, 12, 14. And then 2 more. We have to distribute them to the partially filled subshell right there. So that is your oxygen. What's your bond order for oxygen? How many bonding electrons do we have? 2, 4, oops, that's not it. 2, 4, 6, 8, 10. Is that what we have? Oh, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12, 14, 16. So number of bonding electrons is 10. How many anti-bonding electrons do we have? 6. So what's 10 minus 6 divided by 2? 2. The bond order in O2 is 2. That means that justifies sort of your fluid structure where you draw a double bond when you draw O2. Okay? One thing you'll notice about O2 is it has 2 unpaired electrons. Okay, what does an unpaired electron imply? You would expect O2, the molecule, to be paramagnetic. You would expect it to react to an external magnet. And in fact, O2, okay, is a paramagnetic molecule. Okay, so this was the example for fluorine. The bond order is 1 for fluorine. And how do you explain why O2 is paramagnetic? You have unpaired electrons in the outermost sublevel.